Hi there. Can you charge a 3S or even a 4S lithium-ion battery pack using nothing more than a 5-volt USB power supply? In this video, we are going to test the CN3303 module, which is designed for 3S lithium-ion battery pack. I'll show you how it works, how to connect, what voltage and current it actually produces, and most importantly, we'll test whether it can really charge a lithium-ion battery pack from a 5-volt source. The testing phase will include charging a 3S lithium-ion battery pack, and we will look at the following measurements: input voltage measurement, input current measurement, output voltage measurement, output current measurement, CN3303 module temperature measurement, and charging near the maximum input-output capability. The CN3303 module is a lithium-ion charging module which operates on the principle of boost conversion, that is, voltage up conversion. It has a Type-C interface for connecting your power adapter at the input, or you can directly solder your 5 volts power supply. Here is a SMD inductor used for storing and boosting the input voltage. An SMD diode which provides a rectification function. The capacitors are for filtering purpose, while the resistors help function the CN3303 chip. Here we have a CN3303 IC which provides the boost conversion functionality. A power MOSFET AO4468 is used for switching functionality of the boost conversion process. Near the output, we have two resistors and two SMD LEDs for charge indication purpose. The output can be taken from these 2 points. Also, there are 2 holes on the PCB for mounting purpose. The overall circuit of the module is designed on an FR4 substrate. The module can be operated from 3 to 6 volts input voltage. Similar components can be seen on the 4S module as well, which includes the Type-C interface, SMD inductor, diode, capacitors, resistors, and CN3304 chip along with AO4468 power MOSFET. The only difference between the 3S and 4S module lies in the boost converter chip. The 4S module uses the CN3304 IC, while the 3S module utilizes the 3303 IC, while both of them use the same power MOSFET AO4468. The 4S module also requires between 3 to 4 volts as input operating voltage. Now let's quickly talk about the CN3303 functionality. We apply an input between 3 to 6 volts. This voltage is stepped up to regulated 13.8 volts, but it's pulsating. The pulsed voltage is then rectified to get clean DC voltage for the charging of lithium-ion batteries. The interesting thing about these modules is that the input is only 5 volts, while the battery voltage can be more than 12 or even 16 volts depending upon its version. Here, the important concept is that the charging is not simply to convert 5 volts to 12.6 volts, but it has to control charging current, battery voltage, constant current charging, constant voltage charging, and termination behavior. For example, when a 3S battery is significantly discharged, the charger initially supplies a controlled current. As the battery approaches 12.6 volts, the charger transitions towards constant voltage charging and the current gradually decreases. Let's now discuss the testing setup. We will be applying 5 volts to the input of the module, and we will connect a voltmeter and an ampere meter to measure the input voltage and current respectively. The 3S battery pack will be connected at the output of the module along with volt and ampere meter to measure the output voltage and current. Remember that charging a series lithium-ion battery pack is different from charging a single cell. A charger that regulates the total pack voltage does not automatically guarantee that every individual cell has the correct voltage. Since we already know by the connections that the module is only providing voltage to the terminals of the battery pack and not to each cell individually, that means the cells are not balance charged. That is why it is critical to add a BMS, aka battery management system, to ensure all cells will have equal voltage potential. For a 3S battery pack, a 3-cell BMS is required, while for the 4S battery pack, we need to add a 4S BMS module. For the lithium-ion cells, I will be using this battery holder that can hold 3 cells and it allows easy connection with the BMS module. The ground of cell 1 is connected to the 0-volt point of BMS, while its positive terminal is connected to 4.2-volt point. The positive of cell 2 is connected to 8.4-volt point of BMS, while the positive of cell 3 is connected to 12.6-volt point. The in and out terminals of the BMS is connected to the charging module while keeping one connection open for ampere meter. For the test, I will be using the INR 18650 cells. The cells are now installed inside the battery holder and ready for test. Let's now measure the current voltage of the battery pack before we start the testing process. Right now, the battery pack is at 11.21 volts. So here is the final setup for testing the 3S charging module. Here, I have connected the battery pack to the charging module. The input of the charging module is connected to a 5-volt supply adapter with a voltmeter and an ampere meter to measure the input voltage and input current respectively. Initially, the voltmeter is showing 5.3 volts and the ampere meter is showing 0 amperes as there is no load, but the charging module itself will be consuming some amperes to run, but it is so small in milliamperes that the meter cannot display it. The terminals of the battery pack are also connected to a voltmeter and ampere meter for measuring the output voltage and output current. The voltmeter shows 11.3 volt across its terminals, but the ampere meter is showing 0 amperes as we have not closed the output loop. Since I had only one modular volt ampere meter, that is why I have used a separate voltmeter and the multimeter acting as a current meter for the output measurements. For measuring the temperature of the module, I will be using this digital temperature meter. Let's begin the testing of the charging module by connecting its output with the 3S battery pack. As soon as I connected the battery pack, we can see that the charging process has begun and the battery is being charged with a 1.18 ampere current. The voltage across the battery terminals also increased from 11.3 to 11.7 volts. But more importantly, we can notice that the input voltage has dropped from 5.3 volts to 4.5 volts and the current across the input side of the charging module is 4.03 amperes. This voltage drop is due to the large input current requirement by the charging module. I will be using this temperature probe to measure the temperature of the module components. Let's first test the temperature of the SMD inductor. We can see that the temperature of the inductor is rising very quickly. This is due to the large current being stored inside it and using that current to step up the voltage across the output terminals. Also, the temperature of the CN3303 and the AO4468 chips are not that hot compared to the inductor. Measuring the temperature of the rectifier diode, we can see that the diode is also getting quite hot. Here we can see that the current of the input side has reached up to 4.5 volt amperes and increasing. This increase of current has been so much that the power adapter cannot deliver it, and now the input voltage has been dropped below 4 volts, which is lower than the operating voltage of the volt ampere meter, and it has stopped displaying anything. By disconnecting the load and reconnecting it, the volt ampere meter is now displaying the readings, but it will soon turn off again as the charging module is continuously consuming a lot of amperes from the power adapter. Also, we can see that during this time, since the input voltage of the charging module is dropping below 4 volts, the output current consumed by the battery is also dropping as there is not enough voltage at the input side for the charging module to run properly. And at the same time, the temperature of the inductor is rising continuously and gone above 50 degrees centigrade. One issue that we can clearly see here is that of the inductor. The selected inductor here is not the right one for handling such high currents, and that is why it is getting so hot. Also, there is no limitation of current on the input side of the module, and the boost converter is trying to get more and more current from the adapter, which it cannot deliver, and that is why the voltage is dropping across the input side. Let's apply some thermal paste on the SMD inductor so we can stick the temperature probe onto it. As soon as I place the probe on the inductor, we can see that the inductor is getting so hot and its temperature is going above 80 degrees. Will you use such cheap module for your projects that get that hot? Let me know in the comment section. We can assume that the current across the input side of the module is still above 4 amperes since the boost converter circuit is trying its best to charge the battery with highest current possible. Now it's so amazing to see that the temperature of the inductor has gone above 100 degrees. And I can assure you that this high temperature is spreading across the rest of the components through the PCB. By disconnecting the load, we can see that the temperature stops increasing and the input voltage comes back to normal. This quick drop of temperature confirms us that the heat from the inductor is spreading across the PCB traces and going into the rest of the components on the PCB. By connecting the load again, the boost converter starts charging the battery pack, but soon, due to its increasing current requirements on the input side, we are looking at the same phase where the input voltage drops below 4 volts and the temperature of the inductor rising again. Let's calculate the power at the input and output side at the instance when the voltage at the input terminals is above 4 volts. So, power input is equal to input voltage times input current, and approximately power output is equal to efficiency times power input. So, the input power comes out to be approximately 17.24 watts, and therefore the efficiency will be approximately 74%. A good DC to DC converter has an efficiency of above 90%, but since the inductor is generating so much heat, that explains why the efficiency of this battery charging module has dropped to 74%. As I mentioned earlier, this charging module does not incorporate any current control at the input or output side to ensure the module stays under specific current thresholds. If it had such current control loop, this module would have stayed much cooler and its efficiency would have been much better than what we are getting right now. Right now, I am letting the inductor to keep getting hot and see how far it will go. Also, we can see that the output current has dropped from 1 ampere to zero point 0.5 amperes, which is due to the low voltage across the input terminals of the charging module, and the boost converter is not operating as it should be. If we had connected a battery with say 95% charge, then we would have not found this issue as the module will not require such high currents to charge the battery. That is why I have connected a battery with stored charge of around 89%. Just imagine what would happen if we connect a battery with stored charge of 70% or say 60%. That will make the case more severe and worse for this charging module. Now the temperature of the module has gone above 109 degrees, which is the limitation of the temperature module itself. Let me disconnect the load and let the inductor to cool down a bit. Even after multiple attempts, we are still not on the way of proper charging of the battery pack, and the module keeps getting more and more hot as we keep the battery pack connected. But since the input voltage is dropping, the boost converter cannot function as it should be, and the charging current at the battery terminals keeps dropping. Now, one way to control this issue is by controlling the output current manually by adding a series resistor at the output side of the module. This way, the module will have controlled output current consumption and it may function better than the current state. First, I will be adding this 8 watts 0.1 ohm resistor in series across the load side and see what will happen. The state of the charging module is still as it was before. Let's now try this 25 watts 3.3 ohm resistor. We see some very interesting results. The module has now controlled input and output currents, which is why we can see the input voltage has dropped to only 0.4 volts. And the current consumption at the input side is around 1.67 amperes. Similarly, the current at the output side of the module is only 0.44 amperes and the voltage is 11.7 volts. Also, the temperature of the module is not rising as it was before the addition of the series resistor. This method has allowed us to control the module current and temperature issues, but we got another serious issue here. Can you identify that? Let me know in the comment section if you knew it before I tell you. So, the other serious issue that we are facing now is that the efficiency of the module has now dropped to approximately 63%, which is even worse than before. Previously, we were getting conversion efficiency of approximately 74%. This drop of efficiency is due to the fact that we are wasting some energy in the output series resistor as heat, which is not being consumed by the battery at all. Even now, if I try removing the resistor and connecting the battery directly with the charging module, it is still consuming a lot of current and generating a lot of heat across the inductor. We can see that the battery is getting charged very slowly due to the low efficiency of the module. Let's try another resistor here, which is 1.2 ohms. This will allow us a bit more current passage as compared to the 3.3 ohm resistor. Now, we see that the input voltage is still above 4 volts, but the temperature is again rising slowly. Some of you might have thought that when the inductor is getting hot above some point, then the module suddenly starts getting more current from the power adapter. I was also thinking in the same direction, but this 1.2 ohm resistor tells us its opposite. The rise of the temperature is not the issue here, due to which input current increases so much. We can assume that the 1.2 ohm resistor is now getting quite hot since it is controlling the output current. Here, we can see that as soon as the voltage at the output terminals reaches 12.2 volts, the BMS kicks in and stops the charging process. We know that the BMS should have stopped the charging process at around 12.6 volts, but it has kicked in at 12.2 volts. And we can assume that this 0.4 volts difference might be due to the output series resistor and some tolerance of the BMS itself. What do you think about this 0.4 volts? Let me know in the comment section. Now, if I try to disconnect the battery from the charging module and reconnect it, it will still not start the charging process again, because the BMS will allow this only if the battery voltage drops below its threshold value. By measuring the voltage across the battery terminals, we can see that it has a voltage of 11.3 volts, where the BMS should still keep charging the battery pack, but we can see of this as some programmed error on this cheap BMS. Also, the module output is now around 13.8 volts while the BMS is in no charging state. I have tried to start the charging process again by turning the power adapter off and back on, but since the BMS state is in no charging state, we cannot start the charging process again until we add some load on this battery to drop its voltage. Here I conclude this experiment, and if you ask me, I will never use such a cheap, unreliable and low efficient module for charging any of my 3S battery packs, as it might get fired during the charging state due to excess heat. What do you think of this module? Let me know in the comment section. If you have enjoyed this experiment, then please press the like button, subscribe to my channel, and I will come back again with another interesting experiment. See you later.